In this video, I wanted to walk you through the Matlab solution for the Module 4 homework, and then you can modify that in the way that I asked in the Module 4 homework assignment on Canvas. All right, so if you go and you go back and look at the problem statement talked about a etching machine, to make circuit boards, and it said that there was a transfer function h of s. I don't think they specifically said h of s. He gave an output p of s. Okay, but let's think of it as a transfer function h of s, and this is given. And if you take the semicolon out and run that, you will see this is the answer. Okay. From there, you were asked to produce the poles and the zeros of the system. And so you can do that using the num-den command, symbolic command in Matlab to separate out the numerator and the denominator. And so here I found the roots of the denominator, and of course that gives you the poles, okay? And so if you're also looking for the zeros, you'd have to repeat that for the zeros. Okay, next, find the step response of the system. If you apply a unit step, that means capital R. R of t is unit step. Capital R of s is 1 over s. And then we know from Laplace transform theory that the output P is just h times R. All right, so here we have our output transfer function for the output signal, and we can do the inverse Laplace transform. Okay, then you were also asked to compute the final value of the output, and I wanted to show you that you could do that symbolically as well. You can just take the limit of p, the variable of interest is t, let that go to infinity, and you get a final value of 1 in this case. All right, and the assignment also asked you to plot P, and what we're interested in here is the rise time. All right, so remember, we're trying to get this etching machine to move from 0 to a certain point, okay? And we wanted to do it reasonably fast, all right? So you see here it moves from 0, I can't remember the scale here, it wasn't something like micrometers or something. And so you can see it moves, but it moves relatively slowly, and that's part of the point, okay? So if I published the solutions to this so that you could work on it, but roughly about 0.6 seconds. And I added a part here where I wanted to actually calculate this a little more precisely. So this is another step that I want you to do. All right, take a threshold, all right? So let's take 99% of the final value, all right? And we're going to use that. This is probably not necessary anymore, but we're going to use that, and we're going to solve using a numerical solve. That's what VPA means, variable precision arithmetic, solve. And we're going to set the value of the output P of t equal to the threshold. T is our variable, and we give it an initial starting condition. Okay, if you don't do that, sometimes you get kind of crazy answers if you don't give it an initial condition. So I just eyeballed this and thought it was around 0.6, and then when you rerun that, you get that the rise time in this case is 0.52. Okay, and this would be in seconds. Okay, the second part of this homework assignment, so hopefully you pull up the Module 4 homework, it's called system identification, where basically you're working a Laplace transform in some sense backwards, okay? In general, system identification is harder than that because normally we don't have a great handle on the output function precisely, and so that makes it harder to do this type of system identification. But it's showing the relationship between input and output and how you can use that to determine a system. All right, so in this problem, you were given a time domain output for a specific input. All right, so that lets us calculate the Laplace transform of y, the Laplace transform of the input, and the system identification part is to undo, based on the output and the input, what was the transfer function. Okay, so we can do that algebraically with the Laplace transform. We just take y and you divide by r, and in MATLAB you can simplify that. Okay, so I'll give you a problem like that as well to do for this assignment, so that you can make sure that you do this or know the steps for doing this problem. Okay, the third one that I'm showing you here in this walkthrough is I wanted to show you that you could write some system modeling equations. All right, so I made a lot of symbolic variables because there were a lot of parameters in this problem. But basically, you can write the differential equations, and every time you see, if you look at the solution, every time you see an x, a lowercase x of t, you replace it with its Laplace transform, capital X, okay? In every place you see x dot, you replace it with s times cap x, all right? And similarly for y of t, y dot of t would be here, all right? And you essentially write these equations, okay? So part of the point I wanted to make was you did the free body diagram on this problem, you write the equations, okay? And then you can solve the equations symbolically where you don't have to go through a lot of the algebra. Okay, so the way I solve things symbolically is I use the structure form. I say S, this symbolic structure is the answer to solve, all right? And I've defined the equations here and here, okay? So I solve for the structure, and then if I want to pull out components, y is equal to s dot y, x is equal to s dot x, and so I have the answers that come out here. Okay, to help you make a little more sense of this, I also wanted to plot the output here so we could discuss it a little bit. So I made up some numbers. This problem reminds me of those trucks that you see nowadays for construction, where you have a big truck, but then you also have a spring and a mass suspended off that truck in case a car rams into it from the back. It's going to slow down both the car and slow down the transfer of energy into that truck. Okay, so you've probably seen these kind of things. But I'm just going to make up some numbers. So the big truck or the big mass would be larger than the small mass, and then I made up a spring constant and damping constant just to play around with these things, and then to convert from symbolic to an expression that you can do more easily an inverse Laplace transform on. I use this eval command, which takes these parameters and evaluates y at those parameters, so you get a specific Laplace transform. Okay, I did the same thing for x, so you can take a look at these. All right, so from there, I just do the inverse Laplace transform of x, just picking one out. And what you see here is you get x is equal to some constant times t, and then there's this decaying exponential term. Okay, so there's some complex roots that showed up here. That's why you have the sine term and the decaying exponential term. Okay, so I think that makes some sense if you think about it. So you have this system that's set up in the problem. If you hit that with a unit step, you're applying a force that's constant, which causes the whole assembly to move, all right? And it moves with, some constant time, a constant times time, all right? Because of the interaction between the two pieces, the spring and the damper, there's going to be a little bit of oscillation in that movement, especially with the x side. Okay, so there's going to be a little bit of oscillation, and that's modeled by this term. But as time marches on, that goes away, and you just get a constant ramp function for the motion of the coordinate x on that problem. Okay, so if you plotted that, so I have this plotted here over 5 seconds. You can see some of that, it's a little bit of oscillation around a ramp, okay? And I think if you visualize the movement of that system, that would make some sense to you. Okay, so take a look at this, what I've done here, and apply it to the Module 4 homework that I would like you to turn in. I'd like you to turn in the Live Editor file for this assignment.